All right, we're back. We're on page 12 of note 17 of Calc C. We're doing polar areas, kind of a big deal, and it takes a little while to get used to them, but once you're used to them, not bad, right? You guys got to get that sense of like polar areas traced out strangely, right? It's like a kind of a region that shades in as you go around. So like you're used to areas being like this. This polar area is not like that. Polar area is more like this. Okay, so let's see what we can do here. We've got the graph of r equals 0.9, which I guess is this inner circle deal, and then r equals 1 plus 1/10 cosine of 10 theta. I really like that graph. So look at this. It's like a normal cosine curve, right? It starts at a maximum, and then if I were to draw in r equals 1, which I'm struggling with, but I'm trying. If I draw in r equals 1, that's like the axis, and then it just keeps kind of like doing its cosine thing. But the axis that it's basing its cosine-ishness on is actually the circle r equals 1. It's like very cool. Like it still has a sinusoidal axis, sort of. It's still 1, sort of, but it's r equals 1, and then you can deviate 0.1 in either direction from that, and you do it in kind of a cosine way. Definitely cool. So r equals 1 plus 1/10 cosine of 10 theta is the answer to which one is awesome. It's awesome because this is just taking cosine, something that we think we know really well, and like changing it a little bit. And that's kind of neat. So we want the area enclosed by the awesome graph. All right, so now the question becomes, what do we do? Like how long does this take to fully repeat itself? Well, it should be 2 pi. I mean, it takes 0 to 2 pi. I mean, this is 0. And then let's investigate, right? So I think that if I draw just r equals, so I'm gonna draw it up here, I guess. Should really have more space for this, but so here's 1, and we can go up to 1.1, and we can go down to 0.9. And then the period is 2 pi divided by 10, so it's pi over 5. So the increment is pi over 20 because we divide that by 4. So we got pi over 20. So we'll get to pi over 5. So it's pi over 10. I don't know if I really want to do all of those. Well, I guess I do. Pi over 10, pi over 20, 2 pi over 20, 3 pi over 20. And we're going to start, it's cosine, so it starts at a max, then it goes here, then it's going to go here, then go here, and go here. So let's see how this relates to the graph that we're dealing with, right? So this first part here, so this is what I like about polars. Like you get to kind of explore. That part right there is kind of just this. And then the next part here is just kind of this till we get to like that minimum. And then we're going to go, I'll use a different color, I guess. There is going to be like back here. And then finally, we get back to a maximum here. So this graph between 0 and pi over 5 gives me, you know, this whole thing. So I need another pi over 5. So that'd be 2 pi over 5 would do this. And then I need half of that. So another pi over 10. So I'm at 2 pi over 5. I'm going to add another pi over 10 to get here. And if I add pi over 10 to 2 pi over 5, that's 4 pi over 10 plus pi over 10 is 5 pi over 10 is pi over 2. So this, to get from here to here, is pi over 2. So if we do the entire 0 to 2 pi, it's going to give us the whole thing. So I'm going to set up like a couple of things. So I could do, and I think it's the easiest thing, let's call this R1. So if I do 1/2 the integral from 0 to 2 pi of R1 of theta squared, that'll definitely give me the area. But with polar, you always want to do like a little more. You always want to like see if you can really work things out, right? So another thing that I guess I could do is, so what if I did this value here? I'm going to put in some radial lines there, and then there. So what are these radial lines? All right, so I'm basically going minimum to minimum. I'm getting this thing, which kind of looks like an ice cream cone to me. So I want to go from here to here. So that's at pi over 10. By symmetry, this should be negative pi over 10. Okay, so then how many ice cream cones are there? Well, 1, 2, 3, 4, 5. Well, okay, so you get 1, 2.5. You get 2.5 per quadrant, 2.5 ice cream cones per quadrant. And then we need 4 of those, so that's 10. So I think I could also have done 10, 1/2, negative pi over 10 to pi over 10, and then R1 of theta squared d theta. I think this also would have worked. What if I just did half of an ice cream cone? So half of an ice cream cone, also I've decided to call them ice cream cones, would be 0 to pi over 10. And then there's 1, 2, 3, 4, 5 half ice cream cones. So what am I doing? So there's going to be 20 half. So I need to do 0 to, let's write it down. We would need to do 20 of them. 20 of them, 1/2, 0 to pi over 10. I mean, it makes sense that there's twice as many, but like to work it out straight from thinking that there's half an ice cream cone is taking me a little more effort. The reason I think it looks like ice cream cone is the colors that I chose. I don't know why I'm associating those with ice cream, but like I kind of am. So we can see on the calculator, I'll do that at the end, that these three should be equivalent. And all of them should be the area enclosed by that really cool graph, which is like the whole thing. So straight in, all of this, and then there's, 10 of those. Okay, area between the graphs. I mean, I should be able to take any of my answers to B and just subtract off the full circle. So I could do it like this, right? Just two separate integrals. That's r equals 0.9, so 0.9 squared. Or I could do one integral with the same bounds, 0 to 2 pi. And then it's you square, and then you subtract. Square first, subtract second. It's just like when you're finding volumes of revolution. Square first, then subtract. Because you're really doing like big volume minus little volume. And then we want the area of just one small petal in two different ways. So what's one small petal? I think that what I mean by that is like this, the ice cream. So I want to try and find like just that. So what can I do? Well, I don't know why I'm having trouble counting this. There's 2.5, there's 10 of them. So what I could do is I can find, take 1/10 of the area between them, right? So whatever answer I get here, I would just do 1/10. So that's a possibility. So 1/10 of, let's call that answer C. I don't like that. Let's not call it C. Let's call it K. So let's say that this is K when we get it. 1/10 of K, because there's 10 of them. That's definitely going to work. What if we want to do it like directly though? So I mean, I've already set up the negative pi over 10 to pi over 10. So I'm going to go, it should be 1/2 the integral from negative pi over 10 to pi over 10 of the big curve, which is R1, minus the little curve, which is our circle, d theta. Okay, so a lot of calculator punching now. So I'm going to go in and do that. So easiest, let's see, do I have a calculator open? I do. Got to make sure I'm in radians because now I'm like back to teaching in school, and I'm one of my classes used degrees a lot. Really important that you're in radians or nothing makes any sense. So I'm going to store R1 as 1 plus 1/10 cosine of 10t, I think. Okay, and now we're basically checking, right? So 1/2. I think the template's easier than actually typing. Like I'll probably still type because it's a habit that I have. But 0 to 2 pi r1 of t squared. I always use t instead of theta. Calculator doesn't know this, so it's 201 pi over 20. So that's actually, I mean, I guess that basically is one of the ways. I was going to say one of the ways to find a small thing is like if I subtract this. So if I subtract minus 0.9 squared times pi r squared, which is the area of the circle. It gives me this. Okay, let's do 9/10 so that we get like, I want to get the exact value. And then there are 10 of them, so if I divide this by 10, it should give me, this should be one of the answers. So I think that will be the answer to one small petal, maybe. Let's find out. Let's keep going. So I think that's the answer, but we're checking these. So let's do 10 times 1/2, and then go negative pi over 10 to pi over 10. Pi over 10. All right, so there we go. Same answer. Oh, thank God. And we could have gone 20. So it's like, you set them up and you hope and you're pretty sure, but like it's so good when you get the actual thing. You're like, yes. All right, so I'm getting that for all of them. So that's definitely the area enclosed by the awesome graph. I'll write that in. Then when I go back, you'll be able to see it. So that's 201 pi over 200. It's like almost, it feels like almost a circle. I don't know why that feels like almost a circle to me. I mean, it should be almost a circle. It doesn't deviate that much. All right, area between. So 1/2, template, the integral from 0 to 2 pi of r1 of t squared dt minus, did I already do this? I don't know. Integral, well, this is just the area of the circle, 0 to 2 pi of, let's go with 9/10 so that we get an exact value, squared dt. So 39, we definitely did this. I think I was like, oh, there should be another way to do it. Oh yeah, I didn't use a polar integral. I just used the area of a circle, which, is fine. Like sometimes you got to do that. All right, and then I think the answer to the next one is we can do 1/10 of this, so divide by 10, or I think we can do 1/2. I'm gonna do one single integral for this. Integral of negative pi over 10 to pi over 10 r1 of t squared minus 9 over 10 squared dt. I think this will give us the same answer. And it does. Let's write that down. So 39 pi over 2,000. They're really tiny, unless I'm doing them all wrong. But it's like I did it so many ways and got similar and related answers. It seems unlikely that I've done it entirely wrong. But at the same time, sometimes you're like living in this fictitious world of your own making. And I hope I'm not, but you never know. All right, so these are the values that I got. I'm gonna stop this video here. I'll come back in the next one and do this stuff, which I don't know, may or may not be challenging, but it's probably good practice. So I will see you there.